Hello, this is Michael Sulak, and in this video we're going to be working on practice problems for exam 2, which in my class is all about probability. So let's get started. An event that is guaranteed to occur has a probability of 1. Guaranteed means that it will definitely happen 100% of the time, and it has the largest value a probability can ever be, which is 1. The probability of two mutually exclusive events happening at the same time is 0. If we are talking about mutually exclusive events, that means that by definition, they can never happen at the same time. And so the probability of them both happening is 0, just like this. So now if the probability that E occurs is 0.65, then find the probability of E complement. By definition, the complement is everything else. So when you add an event's probability and the probability of its complement, you get 1. When you do a little bit of algebra, you end up with, so if we want to know the complement, then it's just 1 minus the probability of the original event. So in this case, the probability of E complement is So now we have the probability of obtaining heads twice in a row with a fair coin. So we need something to happen twice in a row. So this is going to allow us to use the multiplication rule for independent events. If it's a fair coin, there's a 1/2 chance you end up getting 1/4, 1/4. These are all the same answers, all the same number, 1/4, 0.25, and 25%. So here we have two events, and we're told that they're mutually exclusive, and we want to find the probability that one happens or the other. If we were drawing a Venn diagram and we have a circle representing event A, event B would be entirely separate. And so if you wanted the probability of one or the other, when two events are mutually exclusive like this, you can just add their probabilities together. So all we have to do is take the probability of A and add it to the probability of B, and you end up with 0.7. And you never want to count anything twice. In this problem, we're told that they're not mutually exclusive. We get an overlap between the two. If we added the area of A to the area of B, we end up counting this middle part twice, which we don't want to do. So we'll end up subtracting, adding the probability of A plus the probability of B, but then we need to subtract off the probability of them both happening. 0.6, the combined area in both of these. In this problem, we want to know the probability that both events occur, and when we have independent events, so the probability of A times the probability of B, 0.24. It's less likely that both these events happen than just one happens individually. So for this problem, we're given again that A and B are independent, and we're told the probability of A, and we're trying to find this conditional probability, the probability of A given B. That's what this vertical line means. And you don't actually have to do any math to answer this problem. You just have to understand what independence means. If you have two events that are independent, that means, and this first probability is just the probability of A ignoring B. It's an unconditional probability. If they're independent, then B doesn't have any effect on the probability of A, which is why for independent events, these two probabilities are the same. And interestingly enough, you could think about this switching these symbols. If the probability of A is 0.7, then this probability we're trying to find, the probability of A, if we know that B happens, is the same number. It's still 0.7. Here we have a problem about Steph Curry, who is a basketball player in the NBA, and we are given that he is a 90.3% free throw shooter, and we are asked to find if he shoots 3 free throws. That's really important. We're going to find the following probabilities. To do this, we do need to make an assumption which allows us to multiply probabilities together. This percentage is the probability for just one free throw, and it's the probability that he makes it. If he needs to make 3 free throws, then what that means is that he makes the first, and he makes the second, and he makes the third. And so if his shots are independent, we can just multiply the probabilities of these 3 events happening. We're going to take 90.3%. We're going to multiply it by itself 3 times. We are going to take it to the third power. You get 0.7363. That is the probability that he makes all 3 shots, about 74% of the time. Now we want the probability that he misses all 3, which means that if we want him to miss 3 in a row, we need to take the probability that he misses it times itself 3 times. The chance that he misses 3 in a row is going to be fairly small. It actually ends up looking like this in my graphing calculator. This is scientific notation telling us to move the decimal place 4 to the left. You could write this number here as, and so if you evaluate this and you move the 4 places to the left, so I get my starting 0, and I have 3 zeros in front of the 9. I said this was a small probability. It's only 0.000912. So now we want the probability that he makes the first and then he misses the next 2. And so because these events are independent, his shots are independent, we can just multiply these probabilities together. 0.008496. So now we're trying to find the probability that he makes exactly 1. And the easiest way to do this is to recognize that the number of shots he makes, this is a variable, and this variable happens to be binomial. So when we're working with a binomial random variable, the things that we need to know are the number of trials. In this case, it's how many shots we're working with in total, which is 3. We need to know the probability of a success. A success is whatever we're counting. So the probability of a success is the same thing as the probability that he makes a single given shot. If we want to call this a variable name, we'll call it x. We're trying to find the probability that x equals 1. And you could do this with the formula for a binomial random variable. In our class, we use a TI-83 or a TI-84 calculator, which has a function called binomial PDF. And in that, we give it the number of trials, we give it the probability of a success, and we give it the specific value we want x to equal, which in this case is 1, and we get there's about a 2.5% chance that he makes exactly 1. I'll just point out that it ends up being more likely than this event, the probability that he makes the first and misses the next two. For this event, if we just use an S for him making a shot and an F for him not making a shot, a failure, this event, he makes exactly 1, could happen in 3 ways. These 3 outcomes all have the same probability, and this number here comes from taking that answer we got from part C and multiplying it by 3. So now we want the probability that he makes at least 1. If I think about this variable, the number of shots that he made, and I make what's called a probability distribution for that, well, the most that he could make is 3, the least that he could make is 0, and he could make either 1 or 2 shots. And if we use binomial PDF, we can find the probability that he makes 0 or 1 or 2 or 3. We found the probability that he made exactly 1 earlier. That was 0.0255. I could put that right here. At least 1 means that he makes either 1 or 2 or 3 shots. And so using my binomial PDF function, I'm going to change the x value to either be 2 or 3. And when I change the x value to be 2, I get the probability that x is exactly 2. And when I change the x value to 3, I get the probability that he makes exactly 3 shots. If I want the probability that he makes at least 1, I can add using the exact numbers that I've got here. I end up with 0.9991. You might notice that doing this problem this way required me to find 3 separate probabilities and add them together. If I was trying to find the probability that he made at least 1, but instead of having 3 total shots, I had 10 total shots, I would have to find 9 probabilities and add them all together, which would be a big pain in the butt. So there's another way you can do an at least 1 problem. If you think about at least 1 as being an event, well, then the complement of that is whatever happens if he doesn't make at least 1. At least 1 are these 3 numbers. So what's the opposite of at least 1? Well, there's only one possible outcome, 0. So E complement is making none. And so because at least 1 and none are complements, that means the probability of making at least 1 is equal to 1 minus the probability that he makes none of them. If I could find this probability, then I can find the at least 1 probability by being sort of clever and just using my complement rule. Well, you could either use binom PDF to find this like we did earlier, or I'll just point out that we've actually already found this number. We know the probability that he makes none of them. We've already done this by finding the probability that he misses all 3 of them. That's the same thing as the probability that he makes none of them. They're the same outcomes. Making none or missing all of them are exactly the same event. It's where the English language can be a little bit challenging. And we know the probability. It's right here. So if I took this number and rounded it to this decimal place, I would get 0.001. And what that means is that this probability here, the probability that he makes none, is 0.001. So if I want the probability that he makes at least 1, is 1 minus 0.001, which is the same result that we got earlier. Slightly different because this number was rounded. And so a lot of times if you want to find the at least one probability, you don't actually have to worry about anything else other than the probability of none. And a lot of times that just involves less math. And less math means there's less chance to make mistakes. So now we want the probability that he misses at least one. It's still at least one, but now we're talking about missing, and it can be confusing to think about the English. So let's just go back and look at our probability distribution for the number of shots that he makes. So these are the numbers that we found earlier. You can confuse yourself all day long thinking about the language of this and what to do. And I'm just going to try to get this answer using the complement rule, which is if he doesn't miss at least one, what happens? He misses none of them. So the probability that he misses at least one is 1 minus the probability that he doesn't miss any of them. But we already have that probability. The probability that he misses none of them is the same thing as the probability that he makes all three. And we have that probability right here. So the probability that he misses at least one is 1 minus the probability of him making all three, which you would basically get to if you added these three numbers up right here. If you want to think of a slightly different way to do this problem mathematically, the probability that he misses none, we said, was the same thing as the probability that he makes all three, which means that the event where he makes it needed to happen 3 times. The probability that he makes all three is the probability that he makes a given shot times itself 3 times. And notice that's the same result. It's a thing that I like about math is there's not only just one way to do a particular problem. But I do highly encourage you, if you can, or to think about this kind of a situation. What's possible? What are the probabilities of what's possible? To get these sorts of problems out of your head and onto paper just makes it more likely that you won't be confused. When you're given a problem in words like this, it can be fairly confusing. So the more stuff you can write down, the easier it is to sort through confusion. So continuing on, now we're talking about a new probability experiment. We have a game spinner here, which has one of 10 different numbers on it, and they're all equally likely. You spin this thing, and wherever the arrow lands is the result of our probability experiment. And we have 2 different events here. So I could define them in terms of their outcomes. And an important thing is that because each of these 10 numbers is equally likely, we can find probabilities related to spinning this spinner once just by counting. We don't need to do any fancy formulas. So let's start with this problem, the probability that F happens. We're going to count. How many ways can F happen? There are 4 ways. And how many total outcomes are possible, each one of these 10 numbers. So the probability of F happening is 4 out of 10. Now next we want the probability of F complement. As a reminder, F was these outcomes right here. So F complement is anything that's not F, these outcomes down here. The number of ways F complement can happen is 6 out of the total number of possible outcomes, which is still 10. Now we want the probability of E complement. E complement is any of the other 8 numbers. And so by counting, and then there's still 10 total possible spins here. So the probability of E complement is 8 out of 10. Next, we want the probability of both E and F. Both of them basically means what's in common between these two groups. The only thing that's in common is the 7. So the probability that both of our given events happen is 1 out of 10. Now we want the probability of E or F. The or party is easier to join. So there are 5 of the numbers in our spinner that are either E or F. Honestly, if I was doing this problem, I wouldn't go through and write out all these outcomes like this. I would just go back and look at my spinner and start counting. And if I just start counting, okay, I'm going to count the things that are in E. There's 2 of them. Now I'm going to count anything that's in F. So the 6. I don't need to count the 7 again because I already counted it. The 8 and the 9. So I end up with 5 possible outcomes. Same answer. You could also use the formula, but I prefer to do this type of problem by just counting. So now we want the probability of E given F. And that means that we know F occurred. We know the spin was one of these numbers. That's our given information. So this probability has fewer ways that it can happen. There's only 4 possible outcomes now. There used to be 10 when we had an unconditional probability. But now we have a conditional probability and we have reduced the number of things in our sample space. And so now we want to know, okay, if you want E to happen, that means you need the outcome to be a 7. There's only one way, which means that this conditional probability is 1 out of 4. A formula for where this comes from, some people like formulas. If you're using the counting method, that's what we've done. The number of ways F can happen is 4. The number of ways that both things can happen is just 1. Now we're going to do the probability of F given E. The spin was either a 1 or a 7. So that means that there's only 2 possible outcomes here. And we want to know the probability of getting one of these 4 numbers. If we know that it was either a 1 or a 7, that means that we needed to get that 7. And so the probability of F given E is 1/2. That's why we get the same numerator here but different denominators. So now we want the probability of E given F complement. You know that these are out of the equation. It's only these numbers that are possible now. The probability is only out of 6 things that are all equally likely. And how many of those are E? That's what needs to go on the top here. So if you remember, E was a 1 or a 7. That means that there's only one way E could happen. The probability of E given F complement is 1 out of 6. So now we're going to find the probability of F given E complement, and now we know that E complement happened. So now for this probability, there are 8 total possible spins. How many of these numbers correspond to the event F? The event F was being larger than 5. 6 is bigger than 5, and 8 and 9 both bigger than 5. How many of our possible 8 outcomes are larger than 5? 3 of them. So the probability of F given E complement is 3 out of 8.